Now, what we had before was a general formula for the energy of an electron in any energy level n orbiting a nucleus with atomic charge Z, with Z protons. Realistically, this is the hydrogen atom. If we can ionize the helium atom once, so that there's only one electron on it, we could use it there, and our Z would be 2 instead of 1. For lithium, we have to get rid of 2 of the 3 electrons. So now Z would be 3, and we could make it work for the single electron. We can essentially do what's called the physics of one electron atoms. You might think, well, that's just hydrogen, and it is, but we could ionize the other atoms, the higher atomic number, we could ionize them more and more to keep being able to use this formula. We'll see if there's any use to this later. For right now, let's concentrate on hydrogen where Z equals 1 and see if we can find the ground state energy, so N equals 1. We put in our numbers, the Z and the N basically go away. We get negative 13.6 electron volts. And what that means is if you have a hydrogen atom in the ground state, it'll take 13.6 electron volts of energy to pull the electron completely free from the proton, so to ionize that atom. If instead the electron is in the first excited state, N equals 2, and the energy we find would be negative 3.4 eV. That means if it's in the first excited state, and it of course wants to jump back down to the ground state, it has to get rid of this difference in energy. This difference from final to initial, or initial to final states, is 10.2 electron volts. That's an ultraviolet photon. So any jump to the ground state from a higher state, they'll all be at least this big or more, because every state above the first excited state, this will be a smaller number, so the difference between this and ground will be larger. So they're all ultraviolet. None of these are visible. For visible light photons, the first place we see those, we see transitions from, say, N equals 3 to N equals 2. That would be our first one. If we want to look at, for example, N equals 4 going to N equals 2, we'd say, okay, there's your initial, there's your final. The difference in those energies is 2.55 eV. We could say, well, okay, what frequency is that? Well, we know E equals HF, so we solve for frequency. We get about 6.2 times 10 to the 14th hertz. What wavelength is that? We use C equals F lambda and solve for lambda. And we get 486 nanometers. That's in the blue-green region. So when we go back up and look at this 486 nanometer line comes from an electron that's in the N equals 4 state jumping down to the N equals 2 state. This is what we could draw our hydrogen energy level spacing as, and it's sometimes called an energy staircase. Here's the bottom step, the ground state. The first step up is a long way up. It's 10 EVs and change up here. Then the next one is almost 2 EVs above that, and about 0.7. They start to get closer and closer together. As you get closer and closer together, the 1 over n squared numbers get closer and closer to the same value. So that's why they're getting closer here. As people were trying to figure out what did these spectral lines mean, what they found was there were various geometric relationships between the lines. You could do sort of mathematical tricks on them and group them. And for example, the 4 that you just saw, the visible ones, that's part of the Balmer series. There's one that, and it really represents all transitions to the N equals 2 state, the first excited state. There's another series of lines, if you look at a hydrogen spectrum, where you can connect these various lines mathematically. And the reason you can is they're all transitions to the N equals 3 line. All the transitions to the ground state can be connected mathematically. They're called the Lyman series. Eventually, when people figured out what was going on, you stopped being able to recognize these patterns and get them named after yourself, because it's kind of apparent at this point what's happening. The real physics here is you have quantized energy levels, So the jumps between two energy levels that have very sharply defined values. Um, we can write this in general for the hydrogen atom if we want to find the frequency of light emitted in a transition. We can write it like this. We've got our starting energy, our final energy. The difference in them is the energy of the photon, which we can write as hc over lambda, and we can solve this for lambda. So hydrogen is the most useful case for this, but again, we can make this work with helium that's ionized once, lithium that's ionized twice, beryllium ionized 3 times, etc. Our energies there would look like this. We bring the z squared back. So hydrogen z equals 1, helium z equals 2. Although we can use this as it is for hydrogen, we can look at a different transition here from 7 to 5. We do the same math. We get this wavelength, which is not visible. It's 4,670. What about if we were talking about helium? Well, we'd have a factor of 4 here. Is there any value to this? Because, we don't see things that are heavily ionized in nature. We might see helium singly ionized, but we're not going to find uranium with 91 electrons missing. It turns out that it's still a useful idea, because if you're talking about the electrons in the innermost shell, the ones that are as close as they can be, and really for big atoms that are in the nucleus themselves, this is a useful formula for the energy. Now, the way X-rays get generated is related to this. And really what happens is we know that if we accelerate or decelerate a charged particle, it will radiate photons. That's how we get radio waves, or how we transmit other waves. We're basically shaking electrons back and forth. If we fire electrons at high speed into a material, they will slow down because they interact with the atoms, and they give off a radiation that's called Bremsstrahlung, which is a German word that means breaking radiation. And it's a continuous spectrum. You get the whole range of frequencies. And notice there are a couple of spikes here, which is weird. These are called characteristic X-rays. And what's happening there is this electron flying in knocks into an inner shell electron in the target material. That electron gets kicked out, but some other external electron drops in, and when it does, it emits what would be a spectral line, only in the X-ray region. So there's a particular energy we get out of this transition, just like we get particular energies out of transition in the visible. The most common target for X-ray machines is tungsten. It has Z equals 74. There are always 2 electrons in the innermost shell, but if we wanted to pull one of those electrons out, the other electron, an electron falling in would see the 74 positive charges in the nucleus and then 1 negative charge from the other electron that's about as far away as it is. So we could say the nucleus has an effective Z value of 73 instead of 74. So now let's say an inner shell electron is removed and an electron from the N equals 4 shell of tungsten falls into that hole. So how do we calculate that energy? Well, we say the initial energy is negative 13.6 over Ni squared times Z squared, where Z is our 73. This is going to be a big number. And then we compare the energy in the final state. When we look at these two values, the difference is right at 68,000 electron volts. This is, X-ray energy. The highest X-ray energy comes when the bullet electron that gets fired into the target dumps all its energy into a single photon. We can figure out what that energy is going to be. It's just Q times the voltage on the electron gun. And we've talked about how that might be as low as 30,000 volts for a dental X-ray or over 100,000 volts for a chest X-ray. So if it's 100,000 volts, then the highest energy X-ray that'll be produced can be 100 keV.